What if the flow of time that humans cling to, the arrow that carries every heartbeat and every memory, was never a straight line at all? For as long as civilizations have gazed at the sky, they have sought to tame the mystery of time. To the Maya, the turning of days and centuries was a cycle, repeating endlessly like the wheels of the heavens. In Hindu philosophy, time was vast and eternal, measured in cosmic ages, rising and collapsing like universes breathing in rhythm. The Greeks imagined time as a circle of rebirth, each ending a seed for another beginning. But in later faiths, especially those shaping the West, time hardened into a single path, linear, finite, a march from creation toward an ultimate destiny. Then came the scientists. Isaac Newton, in the 17th century, declared time to be absolute, a silent, invisible stage upon which the cosmos unfolded. It ticked like a perfect clock, impartial and unstoppable, binding the universe to a single rhythm. For 2 centuries, this view reigned unquestioned till Albert Einstein broke it open. With the theory of relativity, time was revealed as no longer fixed, but pliant, inseparable from space itself. The ticking of clocks bent with motion, stretched with gravity, warped near the edge of stars. Time was not absolute. It was woven into the fabric of the cosmos. And yet, despite these revolutions, human minds remain bound to the illusion of time as singular and ordered, marching irreversibly forward. The arrow comforts us, frames our lives in beginnings and endings, cause and effect, past and future. But what if this arrow is only a shadow of something larger, something stranger, something that suggests time may not be one line? The 20th century opened with a thunderclap in the world of physics. The old scaffolding of classical thought was beginning to tremble. Newton's perfect clockwork, cosmos, space, absolute time had seemed eternal. But in 1908, a mathematician named Hermann Minkowski stood before an audience in Göttingen and declared something that would change not just physics, but the very language of reality. He told them, from now on, space by itself and time by itself are doomed to fade away into shadows. Only a union of the two will preserve an independent reality. Minkowski had taken Einstein's young theory of relativity and pushed it further into the abstract realm of mathematics. What emerged was the vision of spacetime, a single four-dimensional stage where events are not simply happening in time, but are embedded within it, like ink fixed on the parchment of the cosmos. Time was no longer a river flowing onward. It was a dimension, stretched alongside length, width, and height. This was a radical fracture in human perception. For centuries, the mind had imagined the present as something fleeting, vanishing into memory. But in Minkowski's geometry, the present was just one slice of a vast four-dimensional continuum, as real as the ground beneath one's feet. Past, present, and future, laid out, interwoven, already there. The arrow of time had become geometry, its flow an illusion of perspective, yet this unification raised a profound question. If time was a dimension, could there be more than one? If space admitted 3 directions, why was time confined to only one? Minkowski's work whispered this possibility, though he himself never pursued it. The early 20th century brought stranger hints still. At the heart of matter, in the experiments of quantum mechanics, the old certainties of cause and sequence began to dissolve. Electrons did not travel neatly from one point to another. They spread like ghostly waves, collapsing into existence only when observed. The quantum world seemed to defy the very structure of linear time. In the famous double-slit experiment, particles behaved as if they could traverse multiple paths at once, their fates determined not just by their journey but by the very act of measurement. Some interpretations suggested that cause and effect might not be chained as firmly as once believed. In the quantum realm, events did not always respect the arrow of time. They appeared reversible, or even untethered from ordinary chronology. By the 1940s, these cracks in the foundation grew darker and more profound. Kurt Gödel, a logician known for unraveling the limits of mathematics itself, turned his attention to Einstein's equations of general relativity. What he discovered was unsettling. Gödel proposed a rotating universe, a cosmos that swirled like a great wheel. In his solution, time itself bent into circles. Within such a universe, a traveler could follow a path through space-time and return, not just to a place, but to the very moment they had left. These were closed time-like curves, mathematical loops where the distinction between past and future disintegrated. Einstein, presented with Gödel's model, was shaken. Here was proof within his own equations that time might not be linear, that the future could connect seamlessly with the past. He admitted unease, confessing that such loops suggested time itself might be an illusion, though our real universe may not rotate as Gödel described. His solution could not be dismissed. It revealed that general relativity, the crown jewel of physics, harbored possibilities that undermined the human sense of time as an ever-advancing line. Each of these discoveries, Minkowski's four-dimensional union, the ghostly paradoxes of quantum mechanics. Gödel's closed curves pointed toward the same unsettling thought: time may not be what it appears to be. By the mid-20th century, scientists found themselves in a paradox of understanding. Relativity portrayed a universe where time was flexible, stretched by speed and bent by gravity. Quantum mechanics described a microcosm where the future seemed to influence the present, and outcomes defied deterministic order. Each theory worked brilliantly in its own domain, yet they resisted reconciliation. The universe spoke in two tongues, and at the intersection of those voices lay the riddle of time itself. Physicists began to whisper about hidden dimensions, not just of space, but of time. The idea was perilous, bordering on the unthinkable. Multiple time dimensions threatened to break causality, to unravel the very notion of sequence. If there were two times, could an event unfold in parallel rhythms, diverging like branches of a tree? Could existence move forward along one axis, while circling endlessly along another? Mathematically, such worlds were possible, yet physically, they seemed alien to intuition. The human mind, forged in the furnace of linear experience, could not easily comprehend them. Still, nature was leaving hints. Relativity and quantum theory, when pushed to their extremes, both whispered that the simple arrow of time might not be enough to describe reality. Astronomers looked further into the heavens, studying the light of distant galaxies, searching for cracks in the uniformity of time's flow. Particle physicists probed deeper into the quantum, where uncertainty blurred the boundary between before and after. The early hints did not vanish, they multiplied. It was as though the universe itself was asking a question: is time singular? Or is it a veil concealing something richer, something layered, something multidimensional? The discovery phase had only begun. Minkowski's declaration, quantum strangeness, Gödel's loops, all of these were not answers, but doorways. Through them, physics was invited into a new terrain, where the human illusion of a single flowing time might dissolve into something far more mysterious. A hidden architecture of temporal dimensions waiting to be revealed. For centuries, humans trusted the arrow of time. It seemed undeniable. A cup falls, it shatters, and it never leaps whole again into the hand. A candle burns down, the wax pools, and the flame cannot be rewound. Ice melts, smoke disperses, lives move forward. Time, in every ordinary sense, has a direction, from past to future, from order into disorder. This was codified in the 19th century as the second law of thermodynamics. Entropy, the measure of disorder, always increases. It became the guiding principle of time's arrow, the deep engine that gave the future its distinction from the past. No law of mechanics had done this. Newton's equations ran as easily, backward as forward, predicting or retrodicting with the same indifference. But entropy introduced something new: irreversibility, cosmic tilt that ensured the universe itself was moving toward greater and greater disorder. Yet even here cracks appeared. Entropy explained why eggs broke, why smoke spread, why stars burned out. But it did not explain why the universe had begun in such low entropy in the first place. Why had the cosmos started so improbably ordered? If disorder was the natural path, then why was the beginning so clean, so pure, so exquisitely arranged. The law that explained the arrow of time also whispered that it should never have been drawn. Deeper still, the cosmos concealed darker contradictions. Black holes, once only imagined, had become a theoretical inevitability by Einstein's equations. These collapsed stars devoured matter and light, their gravity so extreme that nothing could escape. They became the great prisons of the universe, swallowing whatever crossed the event horizon. For decades, it was believed that once something fell inside, it was lost forever, not just the particles, but the information that described them. But in the 1970s, Stephen Hawking revealed a devastating paradox. Black holes, he showed, were not eternal. Quantum effects at the edge of the horizon meant they emitted radiation, tiny sparks of energy that would, over inconceivable spans of time, evaporate the whole away. If this were true, then black holes eventually vanished, leaving behind only empty space. But here lay the crisis. What happened to the information of what had been consumed? Physics forbids the destruction of information. The equations that govern particles, even quantum ones, are reversible. The initial state must always be recoverable, at least in principle, from the final state. But Hawking's insight suggested otherwise. If black holes evaporated into featureless radiation, then the identity of every particle, every atom, every star consumed would be erased. Time, in this picture, was not simply an arrow, it was a shredder. The paradox sent shockwaves. Through physics, if information could be lost, then causality itself unraveled. The past would not determine the future. The chain of cause and effect would be broken. In such a world, time could not be trusted. It might not even be meaningful. For decades, the information paradox stood unresolved, a haunting reminder that the arrow of time might conceal hidden dimensions, where the rules of reality dissolved. And yet, as if mocking human assumptions, the equations of fundamental physics stubbornly refused to choose a direction for time. At the deepest level, the laws describing particles and forces remain symmetrical. Whether run forward or backward, they remain valid. This principle is known as CPT symmetry charge, parity, and time reversal. The universe, when viewed in this mirror of transformations, behaves identically. It is only at the scale of thermodynamics. At the level of entropy, that irreversibility emerges. The arrow, it seems, is not etched into the fundamental laws, but only into their consequences. The cosmos itself may not care whether time flows forward or backward. Only humans, trapped in entropy's current, feel its one-way grip. But if physics, at its deepest levels, is time-symmetric, what then enforces the illusion of linear progression? Some theorists began to wonder, perhaps what we call time is not fundamental, but emergent like temperature, which arises from the motion of molecules, though no single molecule has temperature itself. Perhaps time, too, is a collective. The effect of something deeper. To contemplate such a thing was to edge toward forbidden territory. More than one temporal dimension had long been considered impossible. If time had 2 or 3 axes like space, causality would collapse into chaos. Events could be reordered endlessly, with no stable sequence. Past and future would lose meaning. A universe with multiple times might dissolve into paradox, where outcomes could never be fixed. And yet the paradoxes were already here. Entropy raised questions it could not answer. Black holes shredded information in defiance of physics. Quantum mechanics suggested outcomes that looked backward as well as forward. The arrow of time, once thought inviolate, was cracking at its edges. Some physicists began to reconsider the unthinkable. If time itself was not a single smooth line, perhaps the contradictions arose because the line was too narrow to contain reality. Perhaps the universe was deeper, stranger, richer. Perhaps time had hidden directions, concealed from ordinary perception. Only glimpsed in the paradoxes that tore at modern physics, it was a shocking thought, terrifying in its implications. For if there was more than one dimension of time, then causality, free will, and even existence itself would be reframed. The arrow of time might not be broken, it might never have existed at all. The cracks had opened. The arrow once trusted, now trembled. And through those cracks, the possibility of hidden time began to emerge. By the end of the 20th century, physics had reached a crossroads. Relativity and quantum mechanics had reshaped the very foundations of reality, but they refused to merge into a single framework. The cracks in the arrow of time entropies, paradox, black hole information loss, and the reversibility of fundamental laws remained unresolved. And from those cracks, a radical thought began to surface. Perhaps time itself was too small. Perhaps one dimension was not enough. In mathematics, this idea was not forbidden. Equations were indifferent to whether one, two, or more temporal axes were included. The problem was physical interpretation. For centuries, scientists had avoided the idea of multiple times, fearing that causality would collapse into contradiction. But in the 1990s, a physicist named Itzhak Bars began to ask what would happen if this taboo were broken. Bars, working at the University of Southern California, proposed what he called two-time physics. His suggestion was daring, that the equations describing the universe could be rewritten more elegantly,
more symmetrically,
if two dimensions of time were allowed. In his framework, the forces of nature, from gravity to electromagnetism, became shadows of a higher dimensional order. The familiar four-dimensional spacetime of Einstein emerged as a projection, much like a three-dimensional object casting a two-dimensional shadow in Bars' view. The apparent singularity of time might be an illusion of perspective. Just as a flat photograph cannot reveal the full depth of a mountain, our one-dimensional experience of time might conceal hidden temporal layers. Every physical law we know could be reinterpreted as the echo of a deeper symmetry, one that only makes sense when more than one time exists. The mathematics of two times did more than shock intuition. It hinted that the universe could be more unified than previously imagined. The standard model of particle physics, long seen as fragmented and incomplete, appeared more harmonious under Bars' equations. Complex interactions revealed hidden order. The strange hierarchies of mass and force seemed less arbitrary. It was as though the universe, when seen through the lens of multiple times, arranged itself with a deeper elegance. But Bars was not alone in suggesting that extratemporal dimensions might be real. Theories already grappling with the mysteries of quantum gravity had stumbled upon similar possibilities. String theory, with its vision of vibrating filaments forming the fabric of all matter and force, demanded more dimensions than the four of ordinary experience. In most versions, space expanded into 10 or 11 dimensions, curled and compactified beyond human perception. Time, however, was usually kept singular, one axis, one arrow, and yet certain solutions of string theory allowed more. In higher dimensional formulations, additional time-like dimensions appeared naturally. It's not as arbitrary additions, but as mathematical necessities. Brain cosmology, the idea that our universe might be a three-dimensional brain floating in a higher dimensional bulk, also left the door ajar. In these vast, extra-dimensional spaces, the distinction between spatial and temporal directions blurred. The geometry itself determined which axis behaved as space and which as time. What humans experience as one temporal flow might only be a chosen slice of a much richer structure. In such a picture, the cosmos could be a far larger stage than imagined. Entire regions of higher dimensional reality might run along different timelines, inaccessible to us, but still part of the whole. The fabric of existence might not be a single thread of time, but a woven tapestry, each strand a different temporal direction. For most, such speculation is almost impossible to visualize. Space with its three axes, length, width, height. Familiar. One can imagine walking left or right, forward or back, up or down. But what would it mean to step sideways in time? If time had two axes, how would they interact? Mathematically, one can describe a plane of time just as there is a plane of space. A point in this plane would not be a single moment, but a grid of moments, extending in two independent directions. Being able to move freely within such a plane could trace paths unfamiliar to human thought. What appears to us as past and future might be only one slice of a larger map. The past might not be fixed. It could be revisited along a different temporal axis. The future might not be singular, but branching, accessible by traveling in alternate directions through this higher time. Some scientists compare the idea to the projection of light. A three-dimensional cube, when lit from above, casts a two-dimensional shadow on the ground. The shadow is real, but it is not the full object. Perhaps the one-dimensional time we experience is only the shadow of a higher structure. Flattened by perception, stripped of its hidden dimensions, our lives, our histories, may unfold within this projection. Never realizing the deeper expanse just beyond reach, the implications are staggering. If time truly has more than one axis, then causality may not be the fundamental law we believe it to be. Instead, causality could be an emergent phenomenon, a rule that holds only within the narrow slice of time humanity occupies. Beyond that slice, other sequences, other logics, other flows might govern, but the dangers are clear. With multiple times, paradoxes multiply. How would one define before and after? Could an event loop endlessly without cause? Could every outcome happen simultaneously, along different directions of time? Would the universe even be stable if temporal axes multiplied? Physicists tread carefully here. Most reject the physical reality of multiple times, confining them to mathematical curiosities. And yet each time the paradoxes of entropy, black holes, or quantum non-locality surface, the possibility returns. Perhaps the unease arises not because the idea is false, but because it challenges the deepest intuitions of the human mind. Intuitions forged by evolution to navigate rivers and seasons, not the architecture of the cosmos. Even Einstein confessed that human categories of thought might not be adequate for nature. Time, he wrote, is stubbornly persistent as an illusion. What if that illusion is not simply its linearity, but its singularity? What if the very idea that time has only one direction is the greatest simplification of all? The deeper the investigation, the more the universe seems to whisper that hidden dimensions may be real. Barr's equations, string theories, higher orders, brain cosmologies, bulk each, in its own way, opens a door. They suggest that time may not be the narrow corridor it appears to be, but a vast, many-chambered hall. Humanity, walking its single path, may see only one wall, one doorway, one arrow. The rest lies unseen, waiting in the silence of higher dimensions, and if that is true, then the arrow of time is not broken. The deeper scientists pressed against the boundaries of physics, the more time began to resist the simple story humanity had written for it. What once seemed like a singular thread, weaving past into present and present into future, began to fray. At the heart of the quantum world, the arrow of time no longer pointed cleanly forward. Instead, it curled, dissolved, and at moments appeared to vanish altogether. Quantum entanglement revealed this most starkly. When two particles become entangled, their properties link across distance. Measure one, and the other reveals itself. Instantly, no matter how far apart they are. To Einstein, this was spooky action at a distance. It seemed to violate relativity's most sacred boundary. Nothing, not even information, could travel faster than light.
8.
Experiment after. Experiment confirmed the effect. Here, simultaneity defied linear causality. It was as if entangled particles shared a connection outside the flow of time itself. As though they were not two things separated by space and moments, but one thing extended across multiple presents. The order of before and after dissolved. In entanglement, the universe seemed to speak in a language. Beyond the grammar of time, more unsettling still, was the delayed choice quantum eraser experiment. In it, particles of light were sent through a system of slits and detectors. The choice of whether or not to observe the particle's path was made only after the particle had already passed the slits. And yet the outcome suggested that the later choice reached backward, altering whether the particle had traveled as a wave or as a particle. The present seemed to shape the past. Events already sealed appeared to be rewritten by decisions made afterward, though no paradox was formally created, or no information could be sent to the past. This experiment revealed something haunting. Time, at its smallest scales, does not behave like a straight river, twists and loops, allowing correlations that blur the very notion of temporal sequence. The arrow wavers, uncertain, as if the universe holds within it more dimensions of time than the human mind can grasp. At the scale of the cosmos, another riddle emerged. In the 1980s, physicists proposed that in its earliest moments, the universe experienced a phase of exponential expansion, cosmic inflation. In a fraction of a second, space-time ballooned at rates beyond comprehension, smoothing the cosmos, spreading quantum fluctuations into the seeds of galaxies. Inflation explained much. Why the universe looks so uniform on vast scales. Why space is flat. Why light from opposite ends of the sky matches so perfectly. But inflation raised questions about time itself. Did time flow uniformly during that moment, or were there different temporal regimes hidden beneath the chaos of creation? Some cosmologists suggest that inflation might have been a transition not only in space, but in time where different flows, perhaps even multiple axes of time, could have briefly existed. In such conditions, the ordinary rules of causality might not apply. The universe may have chosen its arrow, collapsing hidden possibilities into the singular flow we now experience. And yet, mysteries of quantum mechanics and relativity remain unreconciled. Each theory is a triumph, which has been tested to precision. And yet, at their meeting point, in the heart of black holes and at the beginning of the universe, they contradict one another. Relativity insists on smooth spacetime, bending under mass and energy. Quantum mechanics demands fluctuations, uncertainty, probabilistic outcomes. When forced together, infinities erupt, equations collapse, and understanding breaks apart. Some theorists whisper that the answer may lie in multiple time dimensions, though terrifying mathematically. Such a framework could explain why quantum events appear to violate causality, while relativity clings to geometric order. With more than one axis of time, entanglement could be understood as movement along a hidden temporal direction. The delayed choice experiment might be less a rewriting of the past and more a traversal of different time paths, converging into the present. Inflation, too, might have been the phase in which multiple times collapsed into one, giving rise to the arrow we now inhabit. To imagine this is to stand on the edge of comprehension. What would it mean for reality if time were not a line but a plane, or even a volume, extending into directions unseen? If such higher temporal dimensions exist, then the contradictions of modern physics may not be contradictions at all. They may be projections of a deeper order, glimpsed only in paradox. Yet such possibilities are dangerous. They risk unraveling. The very concept of causality, the foundation of science itself. Without cause and effect, how could experiments have meaning? Without a sequence of moments, how could knowledge be built? The fear of chaos keeps most physicists cautious, but the universe has never bent itself to human comfort. Again and again, it has revealed truths that shattered assumptions, Earth not the center, time not absolute, matter not solid, reality not fixed. Perhaps in the end, the singularity of time will prove to be another illusion, another simplification born of limited perspective. Quantum entanglement. Delayed choice experiments, cosmic inflation, each pulls at the threads of the arrow. Each suggests that time, as understood by human minds, is too small to contain reality. And if multiple time dimensions are real, then the story of physics has only just begun. The river of time may not be a river at all, but an ocean with currents. Crossing, swirling, converging an ocean in which humanity has only glimpsed the surface. By now, the cracks in the arrow of time had grown too deep to ignore. Entropy whispered of mysteries it could not resolve. Black holes threatened to erase information. Quantum mechanics hinted at influences that crossed the line between past and future. Relativity and quantum theory, though each flawless within their own domain, refused to share the same stage. From this tension, physicists began to imagine what once seemed forbidden, that time itself might not be singular. What appears to us as a single flowing stream could be only a shadow of a greater, more complex reality. Among the boldest was Sackbars, who spoke of two-time physics. In his framework, the equations of the universe gained a hidden symmetry, when extended into a second temporal dimension. The four-dimensional spacetime of Einstein, so solid to human intuition, was revealed as a projection like the shadow of a higher dimensional form. Just as a cube can cast many different two-dimensional outlines depending on the angle of light, the universe observed in one-time physics might be only one shadow of a richer, multi-time existence. Barr's work suggested that many of the arbitrary features of known physics, particle masses, force strengths, and even the coexistence of quantum mechanics with relativity took on new coherence when recast in this higher framework. Two-time physics did not discard what was known. It embraced it, showing it as a partial view of something deeper. To those willing to accept its strangeness, it offered a glimpse of unity, a vision of nature where symmetry extended beyond space into the very structure of time. But two-time physics is not the only lens through which scientists have glimpsed hidden temporal dimensions. In the realm of quantum theory, another idea took root: Hugh Everett's many worlds interpretation, proposed in the 1950s. It sought to explain why quantum events seem to branch, why particles exist in multiple states. Until observed, Everett suggested they do not collapse at all. Instead, every possibility unfolds. At each quantum decision point, the universe splits, creating a branching tree of realities. In this vision, time itself is not singular, but a branching structure, splitting endlessly into parallel paths. Each universe contains its own version of history, its own flow of events. Two inhabitants within each branch, time feels singular, but from the perspective of the whole, it is manifold. The many worlds interpretation does not describe multiple temporal dimensions in the strict mathematical sense. Yet its imagery, the endless forking of reality, feels eerily like an expansion of time beyond one axis. Each branch is a direction, unseen, another strand of the greater weave. If true, this vision reframes choice, causality, and even identity. Every possibility exists, every outcome is realized. Time is not a single line, but an infinite fractal, ever branching, never ending. To walk forward is not to collapse possibilities, but to slide into one of many currents while others continue. Unseen, yet other theories speak not of branching, but of sudden shifts. A modern cosmology? Physicists debate the stability of the vacuum itself, the very ground state of reality. What is called the false vacuum may not be the true lowest energy state of the universe. If so, then space-time itself is precarious. Perched on a plateau of temporary stability in such a universe, a quantum fluctuation could cause the vacuum to decay, tunneling into a lower energy state. If this were to occur, a bubble of new physics would form, expanding at near light speed, rewriting the laws of nature as it consumed everything in its path. Within this picture, one can imagine that what we perceive as time might shift suddenly, leaping to another regime, another flow, another dimension. Our arrow of time might not simply stretch forward, but collapse into an altogether new form. It's unrecognizable to those caught in its wake. The false vacuum raises a chilling possibility that time itself is unstable, that its flow is contingent. Vulnerable to sudden change, a hidden temporal dimension could be the stage upon which such transitions play out. It's invisible until the moment reality itself jumps across it. And yet, some theorists take the paradox further still, suggesting that time is not fundamental at all. In emergent time theories, what humans call time is no more basic than temperature or pressure. Just as heat arises from the random motion of molecules, time might arise from the collective behavior of deeper, timeless laws. In such models, the universe at its most fundamental has no before, no after, no flow. Only timeless equations, describing relationships without sequence. From this timeless ground, what appears to us as temporal order emerges, an approximation that works at macroscopic scales. The arrow of time, the ticking of clocks, the sequence of lives all are emergent. Like the foam on the crest of a deeper still ocean, if time is emergent, then the conflicts between relativity and quantum mechanics may be illusions, artifacts of a deeper order we cannot yet see. Perhaps multiple time dimensions are not hidden directions at all, but different patterns of emergence. Different ways that timelessness gives rise to the experience of flow. In some regions of the cosmos, or in some phases of its history, time may emerge differently with more than one axis, more than one arrow. Each of these models carries its own beauty and its own peril. Two-time physics offers symmetry and unity, but risks collapsing causality. The many worlds interpretation provides a branching richness, but at the cost of simplicity and parsimony. False vacuum decay reminds us of the fragility of our temporal stability, suggesting that time itself may not be eternal. Emergent time theories strip away the arrow entirely, leaving only the haunting possibility that what humans experience as time is no more real than a shadow cast by laws that themselves never change. The question remains, which? Reality? Are these models glimpses of truth, or imaginative scaffolds destined to fall away? Science cannot yet say. Experiments probe the limits, but so far, none has confirmed or denied the existence of multiple times. And yet the very fact that these theories arise independently, from different corners of physics, suggests that the idea cannot be dismissed. Perhaps one day, telescopes scanning the afterglow of the Big Bang will detect signatures of exotic time flows. Perhaps particle accelerators will reveal anomalies hinting at hidden symmetries. Or perhaps the truth will remain forever beyond human grasp, a secret of the cosmos too vast for finite minds. But even in speculation, one truth stands clear. The arrow of time, so trusted, so taken for granted, is not the whole story. Beneath, it lies a depth uncharted, where physics imagines time as richer or stranger and far more profound than the single thread humanity walks. And if any of these models is true, then the universe is not bound to one timeline. It is a vast expanse of temporal possibilities, emetrical, branching, shifting, or emergent. Time, in such a vision, is not a corridor, but a labyrinth, its passages hidden, its chambers infinite, its structure beyond comprehension. In the end, the theories and speculations remind us that the greatest illusion may be not just that time flows, but that it flows in only one way. Beyond the arrow, there may be the lattice. Beyond the line, the web. Beyond the moment, the eternal. The universe does not easily surrender its secrets. Time, in particular, is the most elusive. It cannot be held in the hand, weighed on a scale, or bottled for study. And yet, through the most powerful instruments ever built, humanity has begun to press against its mystery. If hidden dimensions of time exist, they must leave traces, subtle fingerprints imprinted on the fabric of reality. The task of modern physics is to find them in the underground caverns of Europe and Asia. Particle accelerators serve as the most advanced laboratories for testing the structure of spacetime. Machines like the Large Hadron Collider at CERN hurl protons together at nearly the speed of light, releasing energies not seen since the birth of the cosmos. Within these collisions, physicists search for anomalous particles that behave unexpectedly, symmetries that appear broken, energies that vanish into directions unseen. If additional temporal dimensions exist, their influence might reveal itself. Here, perhaps in the form of particles decaying in ways that defy the normal arrow of time, or through violations of CPT symmetry, where the reversal of time no longer produces identical results. Even the discovery of unknown resonances, fleeting shadows of higher laws, could hint that our one-time universe is only a projection of a deeper order. So far, the results remain stubbornly consistent with known physics. But the data is vast, and within its depths may lie the first whisper of hidden time. Beyond the laboratory, scientists turn their eyes to the heavens, where the oldest light in the universe still carries messages from the dawn of creation. The cosmic microwave background, a faint afterglow of the Big Bang, has been mapped with exquisite precision by satellites like COBE, WMAP, and Planck. To the naked eye it appears uniform, yet within its subtle fluctuations, cosmologists search for imprints of exotic temporal structures. If the universe once contained more than one dimension of time, or if time flows differed during inflation, Their echoes might be written in this light. Anomalies in the distribution of temperature, unexplained alignments, or non-random correlations could all hint at a deeper architecture. Some have pointed to curious patterns, the so-called axis of evil, an alignment of large-scale fluctuations, possible signs of hidden structure. Others remain skeptical, attributing such features to chance or measurement. But the search continues, for if time itself has left fingerprints, the cosmic microwave background may be the most ancient record of its presence. Black holes, too, offer a window into the depths of time, at their horizons, space and time trade places. To an outside observer, the fall toward the singularity stretches into infinity, while to the falling traveler, it happens in moments. Within this distortion, some physicists wonder if more than one temporal flow might exist. Could the event horizon encode multiple histories, preserving not only information about matter, but about alternate sequences of time? Stephen Hawking once described the horizon as a surface of no return. Yet more recent theories suggest that the horizon is less a prison and more a holographic boundary, storing the information of everything that enters. If so, then perhaps this information does not simply encode spatial data, but temporal possibilities as well. Black holes may be the universe's most extreme experiment in time laboratories where multiple flows converge, where the hidden architecture of causality is written in quantum code. Closer to human hands, a new frontier has opened: quantum computing. These machines, harnessing the strange rules of superposition and entanglement, are capable of simulating systems that defy classical understanding. Among their most tantalizing applications is the simulation of time itself. Quantum experiments have already mimicked causality loops, where outputs feed back into inputs in ways that resemble time travel. Some groups have tested models of time-symmetric physics, allowing systems to evolve forward and backward simultaneously. While no paradoxes emerge, quantum mechanics ensures consistency. The results suggest that the fabric of reality tolerates temporal structures far stranger than linear flow. In these controlled quantum systems, scientists glimpse shadows of a universe where multiple time directions could coexist, each reinforcing consistency without collapsing into contradiction. Yet, perhaps the most profound instruments of all are the telescopes, those quiet eyes that gather the faint light of the cosmos. The James Webb Space Telescope, launched in 2021, now peers further than any eye has before, capturing galaxies as they appeared in the first 100 million years after the Big Bang. In its data, cosmologists search not only for stars and planets, but for the fingerprints of time itself. If hidden temporal dimensions shape the early universe, their signatures may lie in the distribution of galaxies, in the way light bends around unseen masses, or in the redshift of ancient quasars. Future observatories both in space and on Earth will expand this vision. The European Extremely Large Telescope under construction in Chile will study the spectra of distant stars with precision fine enough to test whether the fundamental constants of physics have shifted across cosmic time, should variations appear. They may indicate that time itself is not uniform, that it bends or branches in ways unimagined. Other proposed missions, like successors to Webb and space-based gravitational wave detectors, promise even more. Gravitational waves, ripples in space-time itself, may one day reveal disturbances not caused by black holes or neutron stars, but by fluctuations in the underlying fabric of time. Such signals would be faint, buried in cosmic noise, but their discovery would be revolutionary. They would confirm that time is not a single dimension, but a manifold, its hidden folds vibrating through the cosmos. Each of these tools, particle accelerators, satellites, telescopes, quantum computers, represents humanity's attempt to probe the unseeable. None has yet revealed the decisive evidence, but each brings the possibility closer. Science advances not in leaps of certainty, but in the slow accumulation of clues, each one a fragment of a larger picture, and as these fragments gather, a new image begins to emerge, that the arrow of time may be a simplification, a projection of deeper laws, that hidden dimensions of time may be as real as the unseen dimensions of space. That what humanity experiences as the steady march of moments may, in truth, be the faintest surface of a far grander structure. The instruments hum, the telescopes gaze, the algorithms sift their oceans of data. Somewhere, perhaps already recorded in the noise of a detector, lies the first trace of hidden time. When it is finally seen, the shock will be as profound as any in science, for it will mean that humanity has not merely misunderstood the flow of time, but its very nature, that the universe is not bound by one timeline, but woven of many, each carrying its own possibilities, each waiting to be uncovered. If time is not singular, if it is not the single arrow humanity has always believed it to be, then what does that mean for the story of existence? The question is not only scientific, but deeply human. It reaches into the foundations of memory, of choice, of meaning itself. For the human mind, memory is the tether that binds identity. The past feels fixed, unchangeable, a sequence of events leading to the present moment. Yet in a cosmos of multiple times, memory may be only one path among many. If the past can unfold along different directions, then memory is not the faithful record of what was, but the record of one journey across the temporal map. There may be other memories, equally real, but forever inaccessible paths unwalked. Histories untold. What would it mean to know that one's childhood could have unfolded differently, not as a dream or an imagination, but as an actual trajectory in another temporal direction? Would memory lose its certainty? Or would it become even more precious, knowing that it represents not inevitability, but the fragile consequence of one among many possibilities? And what of choice? In a one-time universe, free will is already a question wrapped in paradox. Some argue that the future is determined by the past, that the flow of cause and effect leaves no room for freedom. Others believe that choice is genuine, that the future is open. But in a universe of multiple times, the debate grows even more complex. Do human beings truly choose their paths, stepping across different temporal axes? Or do they simply move, like shadows cast by higher dimensional structures, following routes already inscribed in the architecture of reality? If every possibility exists, as in the branching multiverse, then free will may be less about choosing what is possible and more about experiencing one of many paths. Choice becomes a way of sliding through the lattice of time, not creating outcomes, but inhabiting them. This thought is heavy with existential weight. If every path is taken, does that diminish the meaning of any one? If every joy and every sorrow is played out across infinite branches, then is the human story trivial, just one among countless versions? Or does it mean the opposite, that every story is eternal, every choice sacred, every moment a crystallization of possibility that once experienced can never be erased? In philosophy, meaning has often been tied to scarcity, the idea that life matters because it is finite, because moments pass and cannot return. Yet in a cosmos of multiple times, scarcity is replaced by abundance. There are not only the moments lived, but the moments unlived, flowing endlessly along hidden axes. Does this make life infinite in value, or unbearably fragile, as though meaning dissolves when multiplied without end? Some imagine that a multi-time cosmos could free humanity from determinism, offering countless paths instead of one. Others fear it chains humanity more tightly, showing that every possibility is already written, that freedom is only the illusion of moving along a chosen strand. Between these poles lies mystery, the recognition that meaning may not be destroyed by multiplicity, but deepened by it. For what matters may not be whether every path exists, but that this path exists, this thread of time in which a human heart beats, remembers, hopes. Beyond questions of choice and memory lies the greater reflection. What does it mean for humanity to stand within such a cosmos? For centuries, people imagined time as a river, carrying them forward, its current irreversible, its destination unknown. But if time is not a river but an ocean, then existence is not a journey from source to mouth, but a voyage upon vast waters, with currents flowing in many directions. Humanity sails upon one, but countless others swirl beyond perception, shaping the tides in ways unseen. To live in such a cosmos is to accept both smallness and grandeur. Smallness, because the universe is vaster than anyone dreamed, and the human arrow of time is but a shadow upon its surface. Grandeur, because even within this immensity, human experience remains unique. Each path through the temporal ocean is distinct, each consciousness a singular light cast upon the waves. Perhaps the meaning of time is not in its scarcity, nor in its multiplicity, but in the awareness of it. To know that time may be layered, manifold, and infinite is to awaken to a new humility. It is to recognize that life is both fragile and vast, that every choice echoes not into nothingness, but into a greater architecture, and so humanity stands, at the edge of understanding, gazing not at a single river, but at a boundless sea. The stars shimmer above as reminders of age and distance, each beam of light carrying not only the story of space, but the story of time. Every photon, every particle is a messenger from the depths of temporal structure, whispering of currents unseen. In this vision, humanity is no longer a traveler along a narrow path, but a sailor on a limitless ocean. The shores are unseen. The currents are many, the horizon eternal. Some currents flow forward, others backward. Others sideways into directions the human mind cannot yet imagine. To step into this awareness is to embrace wonder. For if time is not singular, then the meaning of existence is not in reaching an end, but in the act of journeying itself in the lived experience of consciousness as it sails its chosen current. The ocean of time is vast, but the wave that carries a single life is irreplaceable. The chapter of science that explores multiple times remains unfinished. The theories are incomplete, the evidence still faint, yet the philosophical reflection endures.
Act 2?
To live in a multi-time cosmos is not only to ask what reality is, but to ask what it means to be human within it. And so, the story closes with an image. Humanity stands not at the mouth of a river, but at the shore of a great ocean. The water stretches into darkness, its surface rippling with unseen flows. Each current is a possibility, each tide a path through time. The wind stirs and the sails rise. The vessel begins to move, carried forward not upon a single stream, but upon an ocean of many currents, each leading to unknown shores. The journey is endless. The mystery remains, and time, no longer a single arrow, becomes the vastest frontier of all.